So my name is Toru Yagi. It's the first one. Yep. I'm from University of Tokyo, and thanks for coming to my presentation, which is about the reformation of pop-in judgment in CTOD standard using the novel Brittle clock propagation model incorporating the logical energy consumption law. And here's my agenda for today, and I'm going to talk about my background of my research first. So pop-in is an arrested Brittle crack manifests itself with a drop in load and increase in clip gauge displacement, which may occur during a CTOD testing. And I hope this clip works, but I don't know how to play this clip. Yep, thank you. So this is the clip of the CTOD testing. Right now it's loading, and then pop-in occurs, and then loading again, and then fractured. And when this pop-in is regarded as a fracture, the fracture toughness of material is determined by point A on this load and clip gauge displacement curve here. But when this pop-in is regarded as insignificant, the fracture toughness is determined by point B here. And the current standard of this pop-in judgment is the load drop ratio of 5%. And this 5% is said to be too conservative because of two reasons. The first one is that there's no experimental study because of the difficulty to produce a test specimen which can ensure the pop-in generation. And there's also a reason, which is that there's no consideration of the difference of loading mode between the CTOD testing and the real structure. So the objective of this study is to investigate the mechanism of formation of pop-in and to improve the pop-in acceptance criteria. And I have two approaches. The first one is using the stress intensity factor, and the other one is the FEM model incorporating the idea of energy dissipation. So for experiment, the specially manufactured welded joint that can ensure the occurrence pop-in is prepared. So here, this NLLS material is the really brittle material, and it is welded surrounded by the base metal and the MGS80, which is the generally used material, so that they are really tough material. And the two types of specimen are prepared. The first one is section notch, which is the reproduction of the real weld with the local brittle zone. And the other one is a surface notch, which is the prepared for reference. The brittle area is fully distributed along the crack tip. So for here, the red area is the area that the NLLS, the brittle material, is welded. And we conducted the bending test and tensile test for both specimens. And it is important to know that the tensile mode is regarded as a real structure, the loading mode of the real structure. And here is the typical results of this experiment. Just the fracture surface and the PVZ curve is shown here. And from the graph here, you can see that there are no section notch specimens fractured completely. And also there are some section notch specimens which had a load drop ratio of more than 10% for the bending mode. And also for the surface notch, there are some surface notch specimens which briefly fractured completely. And to find out how the pop-in crack arrest, we approached this problem by using the idea of fracture mechanics. So we carried out the 2D crack propagation FM analysis, which is the node-release dynamic implicit method. And we evaluated the result by the dynamic stress intensity factor, KD, which shows the strength of crack propagation. And we normalized this KD value by Rose's equation to see the gradient of KD value as the crack propagates. And here's the result. The green one is the bending mode, and the blue one is the tensile mode. So for the bending mode, this KD value, the normalized KD value decreases as the crack propagates. And when the crack velocity becomes more than 400 meters per second, the KD decreases more rapidly from 1 point. And the other hand, for the tensile mode, the KD, so this is a mistake, but the KD is stable or slightly increases. And this is against the experimental result because you can see the all tensile mode specimens for section notch arrested, the clock arrested. So here's my new proposal for the popping judgment, popping mechanism, which is the popping crack arrest by the closing effect of the saddle ligament. So this is it's a kind of the superposition of the KD value obtained by the FM analysis and the K value of the tunnel crack shape model. So the core part of this model is the closure effect by the saddle ligament. So for this model, the popping crack is modeled as a semicircle crack, and this blue line area is the saddle ligament. And this will have a closure effect for this semicircle crack. And this closure effect is calculated by those equations here, so that the width of the local brittle zone is very important, because that when the local brittle zone length is longer, the area of the saddle ligament gets smaller, so that the closure effect will be smaller too. And the important assumption for this model is the minimum clock, the difference of the minimum clock velocity between the bending mode and tensile mode, based on the idea of the plastic strain. Since the plastic strain for bending mode is big enough, the minimum clock velocity of the bending mode can be really close to this static solution. However, the plastic strain of the tensile mode is not that big. From the previous study, the minimum clock velocity for the tensile mode is around like 400 meters per second. So here we set the minimum clock velocity of the bending mode as 10 meters per second, and for the tensile mode we set it as a 400 meters per second. So here is the true KD value, the strength of the clock propagation of the popping clock based on this closure effect. So you can see that the gradient of the decreasing KD value is stronger for bending mode than tensile mode. So this model can explain the experimental result very well. However, this is not a universal, cause we have to set the minimum clock velocity, or we have to, for the local brittle zone has to be like rectangle area. So what I try to do right now is to using the FM model incorporating the energy dissipation. So as you see the energy balance during dynamic clock propagation, as the energy dissipation during the brittle clock propagation increases, the kinetic energy of propagating crack decreases. So which means that when the energy dissipation is bigger, it is more likely for a crack to be arrested. So to apply this idea to the FM analysis, we use the spring model, which is shown here. The energy dissipation is defined to reproduce the brittle fracture in FM analysis. So when the stress between first of all, the stress between the adjacent nodes increases proportional to the crack tip opening displacement. And when the stress achieves the critical fracture stress, the stress between adjacent nodes gradually decreases. And then finally, the spring got divided so that the fracture happened. And here the energy dissipation, the value of energy dissipation is how the stress between the adjacent nodes decreases. So we conducted the FEM cohesive analysis. We carried out the dynamic explicit analysis with cohesive surface, which is one of the surface interaction property. And there are basically two parameters for cohesive behavior. One is damage initiation, which defines the initiation of damage, and the other one is damage evolution, which is a model of progressive failure for cohesive surface. So we set the value of critical fracture stress as a damage initiation, and we set the value of energy dissipation for the damage evolution. And we evaluated the result by the damage index, the D value, which is the overall value of the scalar damage variable. So when D gets non-zero, that means the damage is initiated. So for here, we assume that when the value D gets non-zero, the crack propagates a point. And I just want to introduce the previous study about the fracture surface energy. So the energy dissipation during the brittle fracture It's constituted by a lot, but the main one is said to be the fracture surface energy, which is consumed by creating this fracture surface. And this value is dependent on the fracture surface roughness. So, and this fracture surface roughness is considered proportional to crack velocity. So I reference from the Feinberg's paper, and you can see that the fracture surface roughness is very dependent on the velocity of the propagating crack. But Nakamura found out that the loading mode is important for the fracture surface roughness. As you can see here, when the crack speed gets like 600 meters per second, the fracture surface roughness of the tensile mode gets really bigger compared to the other bending modes. And here's the result for the FMR analysis. With this combination of parameters here, the result was very close to the experiment. So the non-blue area is the area where the crack propagates. And when I took the crack velocity of this model, the crack velocity was 1900 meters per second, which is natural compared to the previous study. And based on the Nakamura study, the energy dissipation is much bigger when loading mode is tensile. So that I set the value of energy dissipation 10 times bigger than the bending mode one. And the result was close to this experimental fracture surface. But I mean, this chapter is in progress. Those values are, I ran the FMR analysis a lot of times and found the most closest one. So those values are not based on the theoretical, not based on theory. So I mean, our goal is to find out like an equation to set the value of energy dissipation. And we think that the parameters will be the crack velocity or the loading mode. And we think that the fracture surface roughness will be a key factor to find out the equation. So for perspective, first of all, the previous study about the fracture surface roughness is based on the experiment of PMMA material. So you have to carry out the experiment with the steel material to check out the tendency of the steel material. And we have to do further analysis, and final goal is to create a brittle fracture simulation with a great reproductivity and improve the popping acceptance standard. Thanks for listening.